Hi, let's continue. To the third case, model with a critical threshold. Doomsday versus extinction. So remember the second model was the logistic model. Okay, for the logistic model, we have dp dt equals to k times p times m minus p. And here m is the limiting population. Okay, so now we consider a population with birth rate beta equals to k times p and a constant death rate delta. And then we'll get the rate of change is beta times delta times p. And then here, because beta equals to k times p and the delta is fixed, you can consider delta is like delta times k over k, and then you can factor out the k. So after you factor out the k, you get p minus delta over k. Okay, now if we call delta over k to be m, then you get the formula becomes kp times p minus m. Can you compare this one to the logistic model? Are they very, very similar? The logistic model, you have kp m minus p, but now for the threshold model, you have kp times p minus m. So it's exactly the negative of the right-hand side, right? So now m is not the limiting population. M is called the threshold population, with the way that population behave in the future depending critically on whether the initial population is less than or greater than m. Okay, so do you still remember the picture of PT versus dp dt of the logistic model is a opening down parabola? So here we still have a parabola, but because the leading coefficient is k is positive, so we in fact get an opening up parabola where the p-intercepts are still the same, 0 and m. Okay, so now you can see for p is between 0 and m, the rate is negative. So we have population decay. When the p is less than 0 or greater than m, the rate is positive, so we have population growth. So the critical points are 0 and m. Okay. So if we look at the direction field, because when p is between 0 and m, we have the solution decreasing. So that's why the solution going down. For p is less than 0 or p is greater than m, we have the rate. The growth rate is positive, so we have solution increase. Okay, so p is 0, p equals to 0 is stable, right? Because solutions are moving towards it. And p equal m is unstable because solutions are going away from it. Okay? And we call m is the threshold population. You can see, depending on our initial value, okay, so if we have initial value p0 is greater than m, what happened? Well, we can see it just blows up to infinity, so population explodes. We get doomsdays in that case. If the initial population is less than m, then what happened? It will just get close to 0, and the limit is 0, so we have the population is distinct. Okay? And if we solve the differential equation analytically, we're not going to do the same thing again, but do you still remember we derived the formula for the logistic model? And what was the formula for the logistic model? Okay, dp dt is kp times m minus p, and the formula is p of t equals mp0 P0 plus m minus P0 e to the negative kmt, right? Now, let's look at the difference. Let's look at our threshold model. You can see we have P minus M, but actually when I fetch out the negative sign, I get Kp times M minus P. See, they're very similar to the logistic model, where now instead of K, I have minus K instead of K. So it means when you see K in the formula, in the logistic model, you just replace K by minus K. So that's why our new formula is MP0 P0 plus M minus P0 e to the, because we replace K by minus K, then minus K become K. So KMT. Well, you might say, oh, are they the same with our formula, the current formula? Oh, yes, they're the same. If you multiply the top and the bottom by e to the minus KMT, then you can see when the numerator, we get this guy, and the denominator, when you distribute it, you also get the resulting guy. Okay, so now we have the formula for the threshold model. Okay, and this formula will be provided in the exam. You don't need to derive it. You just need to know how to use it. Okay, so now let's look at this example 4. Consider an animal population P of t that is modeled by the equation. So here you can see, remember, this is Kp and this is P minus M. So you can tell, well, K is 0.0004 and the M is now 150, right? You compare it to the equation setup, you can figure out the K and M in this case. So find P of t if P0 is 200. Well, we just plug into the formula. Okay, M 150, P0 200, e to the minus K, K is 0.0004, M is 150, T all over P0 200, e to the minus 0.0004 times 150, T plus M 150 minus P0 200. Okay, so what is that? Okay, so let's see. So we get the numerator 2 times 15 is 30. So 30 and then the 3 zeros after it. And then when you multiply by 0.0004 and 150, you get 0.06. 0.06t. And here we have 200 e to the minus 0.06t. And then we get minus 50. Okay, so that is part A. For part B, we just repeat the same process with P0 is 100. So M is 150, P0 is 100. And then e to the, because K and M are still the same, so we have minus 0.06t. And then P0 is 100, e to the minus 0.06t plus M 150 minus P0, which is 100. Okay, so what do we get? We get the numerator, we have 300. Oh, sorry. The numerator, we get 15000 e to the minus 0.06t over 100 e to the minus 0.06t. And then here we have plus 50. Okay. Alright. So now what happened? Okay. So we can simplify it. We can divide it by 50 on numerator and denominator. Then we have 300 e to the minus 0.06t. And then we have 2 e to the minus 0.06t plus 1. Okay. Alright. More questions. What happened when t goes to infinity? Okay, let's look at part A and part B. Okay, so questions? What happened if t goes to infinity? Okay, so let's look at part A. First of all, look at the numerator. Exponential is always greater than 0, right? So when t increase, oh, what happened? Well, the denominator, so the denominator, it could be 0, right? When t increase, e to the minus 0.06 is decreasing. So 200 times that when is like closer to 50, so we get the denominator is getting closer to 0. So that's why, because the numerator is positive, we have a positive number over some number is getting close to 0. So it actually goes to infinity, right? So part A, we have some number over something close to 0. So actually it will give us infinity. And part B, you can see part B, the numerator and denominator are both positive, right? And so now, because they're both positive, and then the numerator, you know, when t goes to infinity, e to the minus 0.06t will goes to 0. Okay, so t goes to infinity to minus 0.06t will goes to 0. That's why our p of t will goes to 0 over 2 times 0 is 0 plus 1. So this is 0. Okay, so for part A, you can see if p0 is 200, it's greater than m is 150. So we get the population explodes. So we get doomsday. Okay, and in part B, we can see that if p0 less than m, the population will extinct. Okay, so it really depends on the initial population and the threshold population, which one is bigger. Okay. Alright, let's look at the last model, harvesting a logistic population. Okay, so in this problem, okay, let's look at example 5. Suppose that the logistic equation dp dt equals to kp times m minus p, where p0 is the initial population. Suppose it models a population of fish in a lake after t months during which no fishing occurs. Okay, so when no fishing occurs, we have the logistic model. Now suppose that because of fishing, fish are removed from the lake. Sorry, not lake. I have a typo here. Removed from the lake at a rate of HP fish per month. Thus fish are harvested at a rate proportional to the existing fish population. Okay, so what do we have now? Okay, so with fishing, our rate dp dt is like what we had or without fishing, but with fishing, the rate is subtract HP because we remove fish from the lake, so we subtract HP per month. So far, so good, everybody? Okay, let's see. Let me play with the numbers a little bit. So here let me use a different color so you can see the difference, what I'm doing. Okay, so here I multiply by multiply by k and divided by k. Can you see now I can factor out the kp? Let's factor out the kp. What's left? M minus b stays, and here what's left? H over k, right? So we can group m minus h over k together and minus p here. So now I can call this guy m hat, right? I can call this guy m hat. So this is like a new m, right? A new limiting population, right? So compared to our formula. Okay. So now let's answer the problem. Part A, if 0 less than h less than km. Okay, we want to show that the population is still logistic. What is the new limiting population? Well, let's see what's the difference. What's that mean? Okay, so let's figure out. Okay, what is our m hat is m minus h over k, right? We can take the common denominator k, then we have km minus h. Remember that k is always positive. And so here, if given h is between 0 and km, then km minus h will be positive. So the numerator is also positive. So we get m hat is positive. So we still get a logistic equation. Okay? And furthermore, so we have dp dt is like km times m hat minus p, right? We still have a logistic equation with now our new limiting population. Okay, our new limiting population is m hat, which is km minus h over k. Okay, and that's part A. So if we don't fish, like we don't remove like so many fish, we still have the logistic equation. Okay, part B. We want to show that if h greater equal to km, we want to show that the population goes to 0 as t goes to infinity. So the lake is eventually fished out. Okay, so if h greater than equal to km, what is m? So m is km minus h over k. We know k is always positive. And km, so km minus h now is less than equal to 0. Ooh, so the numerator is less than equal to 0. Okay? So right now, let's see what happened. Let's separate into cases. So case 1. If h is km, well, then m hat is 0 over k, so it's 0. Then our differential equation is just kp times m is 0, negative p, so we have minus kp squared. Alright, so we can solve this differential equation. We can both sides divided by p squared. And we still have minus k on the right. We integrate both sides. The left, we have p to the minus 2. We add 1 to the exponent. So we have p to the minus 1 over minus 1 is the same as multiplied by minus 1. And on the right, we have minus kt plus c. Right? So we can multiply by negative 1 on both sides. Then we have 1 over p is kt, and then minus c, I can rename a new constant d. Okay, so what is d? So we suppose we have the initial population p of 0 is p0. Then we have 1 over p0, t is 0, so dd is 1 over p0. Okay, so then we have 1 over p is kt plus 1 over p0. Then p of t is 1 over kp plus 1 over p0. You can see what happened. What happened when t goes to infinity? Our numerator is number 1, right? Our denominator goes to infinity. So this guy will goes to 0. And that's what we want, right? Part B, we want to show that p of t goes to 0 as t goes to infinity. So that's the first case. Alright, second case. If h is greater than km, then our m hat is actually negative, right? So we can still use the formula of the logistic models, because when we derive the formula, we didn't require m to be positive. Okay, so we can still use the formula. So p of t is, now m is m hat, p0 over p0 plus m hat minus p0 e to the minus k m hat t. Okay, now what happened? So we can see now here this guy, because m hat is negative, so let me use different color to show you the difference. Because m hat is negative, so minus k m hat is actually positive. Okay, so what does that mean? Well, it means, you know, exponential function. Oops. Okay, you know, exponential function. Exponential function looks like that. So if this is e to the x, okay, when the base is positive, when x goes to infinity, e to the x goes to infinity, right? So that's why this guy, e to the minus k m hat t, actually goes to infinity. And then because, look at this guy, m hat is negative, right? Negative minus p0, so this guy will be a negative number, and the numerator will also be a negative number. But when t goes to infinity, this guy is the dominant term, because this factor e to the minus k m hat t goes to infinity, so it dominates. Okay, so that's why, because the numerator is negative and then the denominator will be negative, because this term dominates. Negative, negative cancel, so the answer will still be positive. So you get a positive number over some number goes to infinity. So the answer is 0, right? So this is when t goes to infinity. So that's why we also get the same conclusion. When t goes to infinity, the population actually will be extinct for part B. So if we remove a lot of fish from the lake, and then the lake will eventually fish out, which makes sense, right? Okay, so that is session 2.1 and 2.2. Don't forget that if you have any questions, feel free to email me. Bye!